Hello there, and welcome to the Sleepy Cosmic Lens. Tonight we drift into the quiet world of winter, a season that reshapes the planet in ways most of us never notice. When the air cools and the light thins, the ordinary world becomes magically unfamiliar. Winter is not just cold weather, it is a transformation written into the very heart of physics, nature and life itself. A season where hidden wonders rise to the surface, where stillness carries its own language, and where the world slows enough for its deeper workings to show through. There is something almost unreal about the way that winter uncovers normally dormant forces. Beneath frost, beneath stillness, beneath the hush in the air, the earth is busy with processes that are as beautiful as they are surprising. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too. One sleepy soul at a time. But for now, just breathe. Allow your eyes to grow heavy and your body to soften, and let the hush of winter carry you to sleep. Let's begin. Some snowfalls contain microscopic particles from space. As snowflakes grow in the atmosphere, they collect more than just water molecules. High above the ground, tiny fragments of cosmic dust are constantly drifting down through the air column. Many of these particles began as bits of comet tails, asteroid collisions, or the fine debris left behind when small meteoroids burn up far overhead. When conditions are right, forming crystals can sweep these particles up, locking them inside layers of ice before they settle to the surface. Later, when snow from remote places is carefully melted and filtered in laboratories, researchers can sometimes recover these alien grains. Under microscopes, they may reveal exotic minerals, glassy beads created by intense heating, or compositions that point to distant origins in the solar system. In this way, winter becomes a quiet delivery system for material that has crossed interplanetary distances. Most of us see only a white blanket on the ground, but hidden inside may be a record of events that unfolded far beyond Earth. Extremely cold weather can create natural sounds that do not exist in warm climates. On the harshest winter days, footsteps in dry, powdery snow can produce a sharp, squeaking crunch that vanishes as soon as temperatures rise. The sound comes from rigid snow grains rubbing and fracturing under pressure, behavior that requires both low temperatures and specific crystal structures. Lakes and rivers locked under ice can emit deep booms, cracks, and echoing pings. As temperature swings cause the frozen surface to expand and contract, these vibrations race through the ice sheet and the water below, sometimes carrying for long distances and creating an eerie chorus in quiet landscapes. Even thin ice on puddles can shatter into chime-like tones if disturbed just right. In extremely cold, calm air, distant noises may also travel farther and sound sharper as sound waves bend and bounce differently in the stratified atmosphere. Together, these effects create a sonic environment that is fundamentally seasonal, a set of sounds that belong only to the cold and fall silent once the world thaws. Winter can cause rivers to reverse their flow temporarily. In certain conditions, a combination of ice, wind, and water levels can push currents in the opposite direction to their usual path. Ice jams are one driver of this behavior. When broken ice collects and lodges in a narrow section of a river, it can act like a temporary dam, backing water up and forcing it to seek another route. If upstream water continues to arrive, the level behind the jam rises, and for a time the surface flow near the obstruction can move upstream, as the system tries to equalize pressure. Strong, persistent wind blowing across wide river mouths can also pile water into inlets and estuaries, raising the water surface enough that gravity briefly favors an inland push. Once the wind slackens, the jam breaks, or the water level adjusts, the river resumes its normal course. To observers on the shore, though, it can look as if the river has defied gravity and changed its mind. The coldest nights can reshape the chemistry of the air we breathe. When temperatures plummet and wind slackens, the lower atmosphere can settle into distinct layers, with cold, dense air pooling near the ground and warmer air sitting quietly above it. This pattern, called an inversion, acts like a lid on the landscape, trapping gases and particles close to the surface. Pollutants from vehicles, heating systems, and industry then accumulate instead of dispersing, and chemical reactions proceed differently in this concentrated cold environment. Certain reactions slow down as thermal energy drops, while others become more efficient because the reactants are held close together. Nitrogen oxides, ozone, and fine particulates can build to levels that alter both the composition and the optical properties of the air, sometimes giving winter haze its own colour and texture. Natural emissions from soil and vegetation also behave differently, rising into an atmosphere that will not mix them away quickly. The result is that the invisible mixture entering lungs on a still, bitter night can be chemically distinct from what fills the same streets on a breezy, mild afternoon. Winter storms can build electrical charges stronger than many summer thunderstorms. In certain intense systems, especially those that produce heavy snow, the turbulence and collisions inside clouds create ideal conditions for separating electrical charge. Ice crystals, sleet particles, and soft hail called grauple bump and rub against each other in powerful updrafts, transferring charge in the process. Over time, regions of strong positive and negative charge grow apart within the cloud, building an electrical imbalance large enough to leap across the gap. The result can be lightning flashes embedded within swirling snow, lighting up a sky that would normally stay dark and muffled during a blizzard. This phenomenon, often called thundersnow, tends to occur in localized, highly energetic storms, especially near large lakes or coastal areas where warm water feeds vigorous convection into cold air. Because snowflakes scatter light differently from raindrops, these flashes can have a distinct appearance and can be harder to spot, sometimes flickering with a diffuse glow within thick snowfall. Freezing temperatures can change how light moves across landscapes. Fresh snow reflects most of the sunlight that hits it, turning open ground into a bright, almost luminous surface that can rival sandy deserts in brilliance. This high reflectivity alters the balance between incoming and outgoing energy, cooling the air just above the surface and influencing how air layers form. At the same time, temperature gradients near very cold ground can change how light bends as it travels, subtly altering the apparent position of distant objects. Under the right conditions, this bending can stretch, lift, or distort horizons and structures, making far-off features shimmer or float. Ice crystals suspended in the air act as tiny prisms and mirrors, scattering sunlight into halos, pillars, and veils of brightness that hover above snowy fields. Even artificial light behaves differently, with city glow traveling farther over reflective snow and low clouds, illuminating the night sky in ways that look markedly different from summer scenes. The combination of altered reflection, scattering, and refraction turns winter into a season where the familiar rules of light seem to shift. Winter can reveal hidden physics that stay invisible during every other season. When temperatures slide far below what we consider normal, familiar substances enter regimes that we rarely see in daily life. Liquids thicken and creep instead of flow. Gases lose energy until their molecules barely move, and tiny forces that are usually drowned out by heat start to matter. At low enough temperatures, some metals allow electrical current to move through them with almost no resistance at all, turning wire into something closer to a perfect highway for electrons. Magnetic behavior can also shift, with materials flipping from one state to another as thermal motion quiets down. Even simple water reveals unusual sides to itself, forming different kinds of ice with distinct crystal structures and mechanical strength. For scientists, winter is an outdoor laboratory that cooperates for free, offering long stretches of cold that would otherwise require complex equipment. For the rest of us, it is a quiet reminder that the everyday world holds behaviors that only appear when the planet turns the thermostat far down. Some regions experience snow that forms without touching a single cloud. On the coldest, clearest days in certain places, tiny ice crystals simply appear in the air, glittering in sunlight, even though the sky remains an uninterrupted blue. This phenomenon is often called diamond dust, and it happens when the air near the ground is extremely cold and still, yet still contains a trace of water vapor. Instead of gathering inside high clouds, the water molecules begin to arrange themselves directly into ice, nucleating around microscopic particles, or forming spontaneously. Each crystal is small, often shaped like a simple plate or needle, and they fall so slowly that the air seems filled with a silent shining mist. Streetlights at night turn these particles into glowing pillars and halos, making familiar streets look unreal. Aircraft, chimneys, or human activity can disturb these delicate fields of crystals, carving paths through them. It is a form of precipitation that blurs the line between weather and an atmospheric optical display. Winter can change the colour of the sky in ways that no other season can. When the sun rides low over a cold horizon, its light travels through a thicker slice of atmosphere before it reaches your eyes. Along that path, it encounters more air molecules, more tiny particles, and in winter, more ice crystals hanging in high layers. Shorter wavelengths, the blues and violets, scatter away more efficiently, leaving behind warmer reds and pinks that wash across the sky at sunrise and sunset. At the same time, cold air can hold less moisture, which often makes the atmosphere clearer and reduces the hazy veil that mutes summer colours. The result is that twilight can look sharper and more saturated, with deep cobalt overhead and vivid bands of orange, crimson and purple near the horizon. In polar regions where the sun may barely rise or set for long stretches, this effect can stretch out into prolonged dawn-like or dusk-like glows that last for hours. High-altitude ice crystals can then refract and reflect this tinted light into arcs, pillars and subtle glows that are rarely seen during warmer months. Freezing air can make normal materials behave like entirely different substances. Rubber that bends easily in summer can turn rigid and brittle in deep cold, snapping with a sharp crack instead of stretching. Plastics that feel tough and resilient may suddenly fracture under loads they would normally shrug off. Metal can contract enough to change the way moving parts fit together, tightening joints, altering clearances, and shifting mechanical tolerances in machines and buildings. Lubricating oils thicken, slowing gears and bearings that usually spin freely. Even everyday objects like glass can respond differently, becoming more susceptible to thermal stress if one part is warmed while another stays frigid. On the microscopic level, cooler temperatures reduce thermal motion inside solids, making atomic lattices less forgiving when they are forced to move or deform. Engineers who work in cold climates have to consider this entire shift in behaviour, selecting materials, shapes and tolerances that will function across a wide range of temperatures. For anyone paying attention, winter offers a visible demonstration that the properties of a material are not fixed traits, but outcomes that depend on environment. Snow can fall in places that have clear skies overhead. This happens when tiny ice crystals form in air so cold and stable that clouds never have a chance to build. The atmosphere near the ground can hold just enough moisture for crystals to assemble on microscopic particles before drifting downward with almost no turbulence to disturb them. The result looks like a gentle glittering snowfall appearing out of empty air. These events are most common in open plains, polar regions, and high-altitude areas where temperatures drop fast and the atmosphere remains extremely dry. Streetlights at night can reveal the falling crystals as countless pinpoints floating in still air, giving the impression that the sky is producing snow even though it remains cloudless. Because these ice particles are so small and lightweight, they can linger for a long time and often settle without forming deep accumulation. They are also sensitive to the slightest disturbance, which means footsteps, passing cars, or even a sudden breeze can scatter them. This kind of snowfall demonstrates that precipitation does not always require towering clouds. It can form quietly in the lowest layers of the atmosphere, when conditions become calm, cold, and clean enough for ice to assemble out of vapor. Winter wind can carry particles far higher into the atmosphere than summer wind. When cold air masses sweep across large regions, they can create powerful pressure gradients that encourage strong upward motion at specific points. Over open snowfields, the wind can lift fine crystals from the surface and inject them into fast-moving layers above. These currents can then transport airborne particles such as dust, salt, or tiny fragments of organic matter far higher than they would reach during warmer months. In winter, the structure of the atmosphere changes as well. The boundary between cold air near the ground and warmer layers above can create zones where winds accelerate sharply, allowing small particles to hitch a ride into altitudes normally reached by more violent summer systems. Once aloft, these materials can drift for long distances, sometimes crossing entire regions before settling. Scientists use this process to study the movement of nutrients and minerals across continents because winter air can carry signatures of soil, vegetation, and sea spray upward and outward. The combination of strong lifting forces and light dry particles makes winter a surprisingly efficient transporter of atmospheric material. Some animals transform their bodies so drastically for winter that they function like new species. Cold seasons force many creatures into states that would seem impossible if they occurred in humans. Some mammals alter the thickness and insulating power of their fur, but the changes go much deeper than that. Several species modify their metabolic pathways to conserve energy, burning stored fat in a slow, controlled way that allows them to survive long periods with limited food. Others lower their heart rates to a fraction of their normal pace, reducing oxygen demand so sharply that their tissues shift into an entirely different mode of operation. Certain amphibians can tolerate ice forming inside their bodies by controlling where freezing occurs and by producing protective compounds that prevent cellular damage. Even birds undergo changes. Some remodel their internal organs, shrinking or enlarging them, depending on whether they need to extract more energy from food or lighten themselves for long migration flights. These transformations are so extensive that the animals behave like altered versions of themselves, optimized for cold rather than warmth. Winter forces biology to reveal its most flexible strategies, showing how living things can reshape their own inner workings when the environment demands it. Deep winter lakes can contain layers of water that never mix. In cold seasons, the surface of a lake cools until it approaches the temperature at which water becomes most dense. Once it sinks, it forms a stable layer beneath lighter water that sits just above freezing. This arrangement can create a stack of layers that refuse to blend even when wind sweeps across the surface. When the lake eventually freezes, the ice cover locks the entire system in place. Light can still penetrate through clear ice, allowing algae and microorganisms to remain active in the upper layers, while deeper zones sit in near total darkness. Nutrients released from sediments at the bottom build up slowly because nothing disturbs them. Meanwhile, oxygen at the surface cannot easily reach the lower waters, leading to pockets with very different chemical compositions, only a short distance apart. These layered environments behave like miniature oceans with their own internal structure, circulation, and seasonal cycles. When spring arrives and the ice melts, the entire column finally mixes, releasing nutrients, carbon dioxide, and other trapped materials into the water above. The dynamics of winter layering shape the biology of the lake for the rest of the year. Freezing soil can rise upward with enough force to move heavy structures. This phenomenon begins when moisture inside the ground migrates toward freezing fronts. As water turns to ice, it expands, forming pockets and lenses that push the surrounding soil upward. The process continues as more water is drawn in, feeding additional growth. Over time, these icy formations can heave the surface by several centimeters and exert significant upward pressure. Buildings, roads, and fences can shift, tilt, or crack in response. This kind of movement is especially common in regions with repeated freeze and thaw cycles, where the upper soil layers fluctuate around the freezing point. Different soil types respond differently. Clays and silts hold more water and therefore experience larger changes in volume. Sandier soils are less prone to this behavior, but can still rise under the right conditions. Engineers design foundations with these forces in mind, often extending them below the deepest expected freeze line or using materials that tolerate movement. For people observing the ground in winter, frost heave is a reminder that the surface is not fixed. It is a dynamic layer that responds dramatically to temperature, moisture, and structure. Winter can shut down entire ecosystems above ground while keeping them active below. Plants may stop growing, insects disappear from sight, and many animals retreat into hidden shelters. But the soil beneath snow remains surprisingly lively. A thick blanket of snow acts as insulation, trapping heat from the ground and preventing sharp temperature swings. This creates a protected zone where microorganisms continue to break down organic matter, releasing nutrients that plants will rely on when they awaken in spring. Small burrowing mammals carve tunnels under the snow, hunting seeds, roots, and each other in a secret world invisible from above. Fungi continue decomposing leaf litter and fallen wood, slowly recycling material that sustains the forest floor. In streams that freeze over, aquatic insects remain active beneath the ice, feeding and growing until warmer water returns. Even plant roots continue tiny chemical exchanges with soil microbes. The visible landscape may look still, but below the surface, a quiet engine of life keeps turning. Winter divides the ecosystem into two layers. One appears frozen in time, while the other maintains the momentum that will propel the landscape into the next season. Snow crystals can grow into dozens of shapes depending on microscopic temperature changes. The structure of each crystal depends on the precise relationship between temperature and humidity, as the crystal forms in the atmosphere. Plates, needles, hollow columns, dendrites, and complex branching patterns all emerge from slight shifts in these conditions. When the air is slightly warmer, crystals may grow broad and flat. When it is colder, they may stretch into long, slender forms. Small fluctuations in humidity influence how quickly different facets grow, shaping the symmetry and complexity of each piece. Because the atmosphere is never perfectly uniform, a single snowfall can contain countless variations. Scientists study these structures to understand atmospheric conditions, since each crystal stores a record of the environment in which it formed. Even within one snowflake, different sections can grow under slightly different conditions, as the crystal tumbles through shifting layers of air. The result is a collection of tiny sculptures shaped by physics, each one formed through a chain of microscopic events that will never repeat exactly. Snow becomes a gallery of natural design built one molecule at a time. Freezing fog can create ice coatings that grow thicker than the fog itself. This occurs when supercooled water droplets hover in stable air and cling to any surface they encounter. When these droplets contact objects such as tree branches, power lines, or fences, they freeze instantly and add a thin layer of ice. As fog continues to flow past, more droplets settle and freeze, producing a buildup known as rime. Because the process can continue for hours, the resulting ice may grow surprisingly thick, even though the fog layer contains very little total moisture. The accumulated ice often forms delicate feathery structures that extend outward in the direction of the wind. These formations can grow into elaborate patterns that look handcrafted despite being created entirely by atmospheric conditions. Unlike clear ice formed from freezing rain, rime ice is porous and structured, making it lighter but still capable of weighing down branches and cables. Areas with frequent winter fog can develop landscapes coated with pale, spiky growths that appear overnight. The phenomenon highlights how persistent small droplets can drastically reshape the environment when temperatures drop below freezing. Winter cold can reveal thermal patterns across the planet that satellites struggle to detect. When the ground cools rapidly at night, particularly under clear skies, different surfaces release heat at different rates. Rocks, soil, vegetation, and built structures all respond to the cold in their own way. These variations create a patchwork of temperatures that can only be observed when everything is exposed to the same intense chill. Researchers use winter conditions to study heat retention, moisture content, and material properties across large areas, since the contrast between warm and cold surfaces becomes more pronounced than at any other time of year. The thermal signatures revealed by winter can show how landscapes absorb sunlight, how cities trap warmth, and how different ecosystems manage energy in harsh conditions. Even wildlife patterns can be inferred from these cold night readings, because animals modify the thermal footprint of the ground in subtle ways. Winter becomes a diagnostic season that highlights differences that remain invisible when the environment is warm and uniform. The quiet clarity of extreme cold acts like a spotlight, revealing hidden structure in the world. Some insects avoid winter death by removing water from their bodies. This strategy, sometimes called freeze avoidance, works by reducing the amount of liquid that could turn to damaging ice. As temperatures fall, certain insects begin converting internal substances into forms that draw water out of their cells. By lowering the water content, they prevent ice crystals from forming. Since there is simply not enough liquid left to freeze in a harmful way, these insects also produce compounds that lower their freezing point, helping them survive temperatures that would destroy most living tissues. During deep winter, their bodies enter a state of extreme stillness. Heart rate slows dramatically, metabolic activity drops to a minimal level, and all motion ceases. Yet, the insect remains very much alive. When warmth returns, the internal balance shifts again. Water re-enters the tissues, metabolism resumes, and the insect continues life, as if months of severe cold were nothing more than a long pause. This remarkable adaptation shows how far evolution can push life to survive conditions that seem entirely incompatible with biology. Snow cover can change the path of storms thousands of miles away. When a landscape becomes coated in bright reflective snow, it sends much of the incoming sunlight back into space instead of absorbing it. This rapid cooling of the surface alters the temperature and pressure patterns above it, creating pockets of cold, dense air that behave differently from the warmer regions around them. Storm systems respond to these differences because they travel along corridors shaped by contrasts in pressure. As the snow-covered region expands or contracts, those corridors shift, nudging storms toward new routes. In some cases, a snow-covered area can act like a giant mirror that cools the atmosphere over an entire region, reinforcing pressure systems that persist for days. This can redirect storms across continents, influencing where moisture falls, how strong weather fronts become, and which regions experience unusual patterns. Meteorologists track snow cover precisely because it creates ripple effects that travel through the atmosphere far beyond the area where the snow actually lies. Winter landscapes therefore become active players in shaping weather, guiding storms that may originate thousands of miles away. Winter nights can carry sound much farther than summer nights. Cold air alters the way sound waves travel, especially when temperatures are sharply different at the ground and above it. On winter nights, the surface cools quickly, while the air a short distance overhead can remain warmer. This arrangement causes sound waves to bend downward instead of dispersing upward into the atmosphere. As a result, noises from far away can reach listeners clearly, sometimes traveling multiple times farther than they would in warm seasons. The quietness of winter nights enhances the effect. Snow-covered ground absorbs some sounds, but it also reduces wind and surface activity, leaving fewer competing noises in the background. Human-made sounds from trains, vehicles, and machinery can seem louder and clearer, and natural sounds such as cracking ice or distant animals can carry surprising distances. This seasonal shift demonstrates how temperature changes reshape not just landscapes, but also the invisible structure of the air. Winter becomes a natural amplifier that reveals a different acoustic character of the world. Ice crystals in the air can build halos and pillars, rarely seen in warmer months. When sunlight or moonlight passes through suspended ice crystals, the crystals can refract and reflect the light into geometric forms. In winter, especially during extremely cold and stable conditions, the atmosphere can fill with millions of tiny crystals shaped like plates or columns. These crystals orient themselves as they drift, often settling into gentle alignment with gravity. When light enters one side of a crystal and leaves through another, it bends at precise angles, creating arcs, rings, or tall pillars of brightness above streetlights. Some formations appear as glowing circles around the sun or moon, while others create sharp vertical beams that look like illuminated towers rising from the ground. The shapes depend on the crystal type and the angle of the light source. Winter provides the perfect environment for these displays because cold air can support numerous crystals without melting them. The result is a set of visual phenomena that turn familiar skies into scenes filled with optical geometry. Frozen oceans can create booming sounds that travel long distances. When sea ice forms across wide stretches of ocean, it behaves like a flexible sheet that responds to stresses from tides, currents, and temperature changes. As the ice expands or contracts, it can fracture suddenly, creating cracks that release bursts of sound. These noises range from sharp pops to deep resonant booms that can echo across the frozen surface. Some events occur beneath the ice when trapped pockets of water shift, or when pressure redistributes along ridges where the ice has piled upon itself. Because sound moves efficiently through both ice and water, these vibrations can travel for remarkable distances. In polar regions, explorers and researchers often describe long drawn-out groans and rumbling tones that seem to come from nowhere, created by slow movements of the pack ice. Each tone carries information about thickness, temperature and stress within the frozen landscape. The frozen ocean becomes a giant resonating body that communicates its own constant adjustments. Winter temperatures can shift the boundary between land and atmosphere. As the ground cools deeply, it alters the exchange of heat and moisture between the surface and the air. A layer of very cold, dense air settles close to the ground, forming a stable boundary that resists mixing with the air above it. This boundary changes how winds behave, how humidity moves, and how gases circulate. In some regions, it can trap pollution or moisture, creating fog, haze, or frost. In others, it can produce extremely clear air with long-distance visibility. Soil that freezes also stops releasing the moisture and heat it normally would, which means the atmosphere loses a major source of input. Over time, a new balance forms between the land and the sky. Winter therefore redraws the interface between Earth and its atmosphere by changing the rules of heat and moisture exchange. This shift affects everything from storm formation to regional climate patterns, and remains one of the most significant seasonal transitions on the planet. Snow can insulate the ground so effectively that plants survive intense cold. A blanket of snow traps the warmth stored in soil and prevents rapid temperature swings. Even when the air above plunges far below freezing, the ground beneath deep snow can remain close to the freezing point, creating a stable environment where roots and microbes continue limited activity. This insulation protects plant tissues that would otherwise be damaged by extreme cold. In forests and meadows, snow cover becomes a protective layer that allows seeds, dormant buds, and root systems to survive conditions that the open air cannot tolerate. The insulating effect also creates a unique subnivean space, a narrow world between soil and snow where temperature remains steady and creatures can move safely. The survival of many ecosystems depends on this simple physical property. Without snow acting as a thermal shield, winter would damage or kill vast numbers of plants long before spring arrived. Snow therefore plays a deeper role than simply covering the landscape. It becomes part of the biological infrastructure that keeps entire habitats intact. Frozen rivers can crack in patterns that mimic continental crust. When a river surface freezes, it forms sheets of ice that continue to shift in response to current, temperature, and pressure. These sheets can fracture into plates with sharp boundaries that resemble miniature versions of tectonic plates. As temperatures fluctuate, the ice expands and contracts, producing ridges where sections collide and channels where they pull apart. These movements create networks of cracks that branch, intersect, and reorganize over time. Observers may see long straight splits that run for great distances, or intricate webs of smaller fractures that spread across the surface. Beneath the ice, flowing water adds complexity by pushing upward against weak spots or eroding support from below. The result is a dynamic system where the frozen surface behaves like a cold analogue of Earth's crust. Scientists studying ice mechanics use these natural patterns to better understand stress distribution in solid materials. For anyone watching from the riverbank, the frozen surface becomes a living map of tension and release. Winter sunlight can reflect from snow with a brightness that rivals desert sand. Fresh snow has a high albedo, meaning it reflects a large portion of the sunlight that reaches it. Because each grain of snow contains countless facets, light scatters in many directions, producing a brightness that can surprise even people accustomed to winter climates. This intense reflection affects energy balance by cooling the surface further, creating a feedback loop that helps preserve the snowpack. For humans, the brightness can be strong enough to cause temporary discomfort or even snow blindness if eyes are not protected. Animals in snowy environments adapt with eyelid shapes, pigmentation, or behaviors that reduce exposure. The reflective power of snow also changes how landscapes look from afar. Cliffs, forests, and mountains gain higher contrast, and distant features become easier to distinguish. Snow-covered ground transforms winter into a visually intense season despite its low sun angle. What appears at first as a simple white surface is actually a complex array of reflective structures that redirect sunlight across the environment. Cold air can sharpen long-distance visibility far beyond what is possible in summer. Low temperatures reduce the amount of moisture that air can hold, leading to dry, clear conditions when skies remain calm. With fewer water droplets and less particulate content, light passes through the atmosphere with minimal scattering. As a result, distant mountains, buildings, or landscapes appear sharper and more defined than they do in warm, hazy months. The stability of winter air also contributes to this clarity. Without strong rising currents or turbulent mixing, the atmosphere becomes layered and still, creating a natural telescope effect that improves long-range viewing. In regions with snow cover, the reflective ground helps illuminate distant slopes or ridges, further improving visibility. These conditions allow people to see landmarks that may remain hidden the rest of the year. Winter therefore becomes a season of unexpected visual reach. What the cold takes away in comfort, it offers back in clarity, revealing far horizons that summer haze often obscures. Winter cold can slow biological processes to near suspension. As temperatures drop, chemical reactions inside living organisms proceed more slowly, reducing energy demands and altering how cells function. Many species rely on this slowdown to survive harsh conditions. Some reptiles and amphibians enter states where movement stops almost entirely and heartbeats become faint. Microorganisms reduce their activity to minimal levels, conserving resources until warmth returns. Even plants participate in this shift. Their cellular machinery changes, water content decreases, and growth halts. This suspended state protects tissues from freezing damage and prevents metabolic stress. The slowing of biological processes also influences ecosystems as a whole. Predators hunt less, prey move less, and the flow of energy through food webs becomes subdued. When spring arrives and temperatures climb, the renewed speed of chemical reactions sparks a surge of activity. Winter acts as a natural switch that resets life across large regions, demonstrating how deeply temperature controls the rhythm of living systems. Snow can grow layers that store precise records of weather over time. As snow accumulates through winter, each storm leaves behind a distinct layer shaped by temperature, humidity, wind, and crystal type. Over days and weeks, these layers compress but remain separated by subtle differences in texture, density, grain size, and trapped air. Researchers can dig snow pits and read these layers like pages in a seasonal archive. A fluffy layer might reveal a calm snowfall, while a dense rounded layer can signal strong winds that pack the crystals together. Thin crusts may appear when sunlight briefly warms the surface, before temperatures plunge again. Dust or pollen that settles on snow forms thin lines that help identify the timing of specific weather events. Deeper down, the layers slowly change as snow transforms under pressure, but patterns still remain. Each winter leaves behind its own fingerprint of storms, warm spells, cold snaps, and atmospheric events. This layered structure becomes the foundation of glaciers in regions where snow survives year after year. What begins as delicate snowfall gradually becomes a long-term environmental record, stored in frozen form. Ice can form floating sheets that collide and grind like miniature tectonic plates. When rivers, lakes, or coastal seas freeze, the ice does not behave like a uniform slab. Instead, it forms separate sections that shift in response to currents, wind, and temperature changes. These pieces can drift toward one another, colliding along edges that rise into ridges or buckle under pressure. Sometimes one sheet slides over another, creating layered formations that resemble small versions of subduction zones. In places where the ice pulls apart, long open cracks called leads can appear, revealing water beneath. These dynamic movements continue throughout the season, shaping the frozen surface into a constantly changing mosaic. Scientists who study ice mechanics examine these interactions to understand how stress moves through solid materials. Indigenous communities and experienced winter travelers also learn to read these patterns, since the arrangement of ice sheets can reveal safe routes or dangerous conditions. The shifting plates remind observers that even frozen water is not static, It behaves like a living surface that reacts to forces from both above and below. Winter clouds often contain more ice than water. Cold season clouds form in conditions where temperatures fall low enough for water droplets to freeze into tiny crystals. At these temperatures, even droplets that remain liquid can be supercooled, ready to freeze at the slightest disturbance. Once ice begins to form, it grows at the expense of the surrounding droplets because water vapor attaches more easily to solid surfaces in cold air. This process increases the ice content until large parts of the cloud consist of crystals rather than liquid. These crystals may take the form of plates, needles, columns, or branching shapes depending on the exact temperature. They interact with sunlight in ways that liquid droplets cannot, creating halos, arcs, and other optical effects. The presence of ice also changes how precipitation forms. Crystals can gather moisture, grow larger, and eventually fall as snow or sleet. Even when the ground remains above freezing, the cloud itself may still be dominated by ice. Winter clouds therefore operate with a different internal chemistry than summer clouds, leading to unique visual and weather patterns. Cold weather can dramatically amplify the smell of certain chemicals. When air temperature drops, the atmosphere becomes denser and less turbulent, which slows the dispersal of airborne molecules. At the same time, the human sense of smell may become more sensitive because cold air allows odor molecules to remain concentrated near the ground. Subtle scents that would drift away quickly in warm weather can linger in winter. This effect is noticeable near forests, industrial areas, and even residential neighborhoods where the smell of wood smoke, soil, or vegetation becomes sharper. Chemical reactions also proceed more slowly in cold conditions, which means some compounds remain unchanged for longer periods and can travel farther without breaking down. Frost and smoke can trap odor temporarily, releasing them when sunlight warms the surface. These combined effects create a seasonal pattern where the same environment carries a different scent profile depending on temperature. Winter does not simply mute the world, it enhances certain sensory signals by altering the chemistry and movement of molecules in the air. Frozen lakes can form rings and circles that scientists still study. During winter, some lakes develop mysterious circular patterns on their ice or water surface that appear without clear warning. These rings can span large areas and often have sharp boundaries that stand out against the surrounding ice. Several processes can create them. Warm springs beneath the lake can send heat upward, thinning the ice in circular shapes. Rotating eddies of water can form beneath the frozen surface, carving subtle spirals that appear when viewed from above. In some cases, methane rising from the lakebed can create circular melt zones. These features can persist for days or weeks before fading. Because each lake has unique currents, sediment patterns, and thermal behavior, the rings vary in shape and size. Researchers track them with drones and satellite imagery to uncover the processes behind them. For people encountering them from shore or the air, the circles look almost intentional, as if drawn by a hidden hand beneath the ice. Winter storms can move heat between continents. Large-scale weather systems that form in cold seasons can tap into warm ocean currents, redistribute that energy, and send it across vast distances. Storms can draw heat from regions with warm surface water, carry it into cold air masses, and release it through condensation as clouds form. The resulting interaction changes both the structure of the storm and the temperature patterns downstream. These processes contribute to shifts in jet stream pathways, influencing how warm or cold certain regions become. Winter storms therefore play a role in balancing global heat distribution. They act as movers of energy, pulling warmth from some areas while delivering cold to others. This movement affects ocean temperatures, atmospheric moisture, and even long-term climate trends. Each storm becomes part of a global cycle that exchanges heat between land, sea, and air. Winter is not simply a local event, it is a participant in planetary-scale energy transfer. Snow that falls on the ocean behaves differently from snow that falls on land. When snow reaches open water, it encounters a surface that absorbs heat and moves constantly. Much of the snowfall melts quickly, creating a thin layer of fresh water that floats above the denser salt water. This layer can change the temperature and salinity of the surface, influencing wave behaviour and how heat escapes from the ocean. When conditions are cold enough for sea ice to form, snowfall becomes part of a more complex system. Snow sitting on top of thin ice can push it downward, allowing seawater to flood the snow layer. When this mixture freezes, it produces a distinct type of sea ice that differs from the ice created directly from ocean water. Snow also insulates sea ice, slowing its growth but protecting it from melting during sunny winter days. These interactions shape the thickness, strength and movement of ice across polar regions. The meeting of snow and salt water creates outcomes not seen on land and affects both weather and ecology. Winter can create natural lenses made of ice that bend sunlight. When water freezes into clear, bubble-free ice, it can form shapes that refract light in precise ways. Droplets that freeze into spheres on branches or rocks become tiny lenses that magnify patterns beneath them. Larger curved surfaces on frozen lakes can bend and focus sunlight into bright patches that dance across the ice as the sun moves. Even small variations in the thickness of clear ice can create optical distortions, stretching or compressing objects seen through the frozen layer. Under certain conditions, melting followed by rapid refreezing can produce smooth domes of ice that act like magnifying glasses. These natural lenses reveal fine details of the ground or water below, creating views unavailable at any other time of year. People walking across clear lake ice may see stones or plants distorted into unexpected shapes as the ice bends the light passing through it. Winter thus becomes a season filled with unintentional optical experiments created by the interaction of sunlight and frozen water. Frozen ground can trap gases that reactivate when thawed. During winter, soil freezes from the surface downward, locking moisture and gases in place. Microbial activity slows sharply, allowing organic material to sit largely undisturbed. As the freeze deepens, carbon dioxide, methane and other gases that would normally escape remain sealed within ice pores. When spring warmth finally returns, these gases are released in a rapid pulse as the ground thaws. In wetlands and tundra regions, the effect is especially strong because large amounts of organic matter accumulate through the year. Once thawed, microbes reawaken and resume breaking down this material, accelerating gas release even further. This cycle influences local ecosystems by altering soil chemistry and moisture patterns. It also affects the atmosphere as thawing soil becomes a temporary source of gases that were stored all winter. The contrast between silent frozen months and the surge of activity during thaw demonstrates how deeply winter controls the movement of energy and matter through the ground. Snow grains can evolve into new shapes long after they fall. Once snow settles on the ground, it does not remain static. Temperature gradients within the snowpack cause water vapor to move from warmer layers near the ground to colder layers near the surface. As this happens, individual grains change shape through a process called metamorphism. Rounded grains can grow into larger angular forms or reshape into faceted crystals. In some cases, the grains bond together, forming stronger layers. In others, the structure becomes weaker and more prone to collapse. These transformations depend on temperature, depth, sunlight, and the amount of trapped air between grains. Over time, the snowpack becomes a layered structure with distinct mechanical properties. These changes influence everything from avalanche risk to how well the snow holds heat. Snow on the ground is therefore not a simple frozen blanket. It is a constantly evolving material shaped by subtle exchanges of energy and moisture. Ice can build delicate structures on plants that mimic mineral formations. During winter, supercooled droplets floating in cold air can freeze instantly when they touch a surface that is even slightly colder than their surroundings. When this happens on branches, leaves, grasses, or seed heads, it creates formations that resemble the intricate growth of minerals. Instead of growing downward with gravity, the ice forms outward along the direction of the airflow, building feathery or blade-like projections that appear almost crystalline. These structures depend on humidity, temperature, wind speed, and the shape of the plant. Even a slight shift in breeze can redirect growth, creating layers that curve or twist as new droplets freeze. Because plants have countless small ridges and textures, the freezing droplets attach in patterns that look surprisingly geometric. The result is a landscape transformed into a series of temporary sculptures. Early morning sunlight reveals each structure as light refracts through the ice, creating a delicate glow before rising temperatures or shifting winds remove the formations. This phenomenon demonstrates how a simple interaction between plants and cold air can produce patterns that seem carefully crafted rather than naturally formed. Winter pressure patterns can shape entire regional climates. Cold season atmospheric pressure systems control the movement of air masses across continents, influencing temperature, rainfall, and storm tracks for months at a time. These systems form because winter cooling strengthens the contrast between warm and cold regions, creating zones where air becomes dense enough to sink and spread outward. The position and size of these pressure centers determine how moisture moves, where storms form, and which regions become dry or wet. In some places, a persistent high-pressure system can lock cold air in place and prevent warm air from arriving. In other regions, low-pressure patterns guide storms toward coastal areas while leaving inland locations dry. Small changes in the strength or position of these systems can reshape entire seasons. Scientists study these winter patterns because they influence everything from ocean circulation to agricultural conditions. They reveal how a subtle shift in air pressure can determine whether a region experiences heavy snowfall, mild conditions, or weeks of quiet, frigid weather. Frost can form patterns that map airflow across a window. When moist indoor air meets a cold window pane, tiny droplets condense and freeze, turning the glass into a canvas shaped by temperature and airflow. As frost begins to grow, it follows invisible gradients created by the flow of air near the glass, forming branches, spirals, and ridges. Warmer areas remain clear for longer, while colder spots attract more ice. The direction of airflow from heaters, vents, or even a person moving through a room can redirect the frost pattern entirely. Microscopic imperfections on the glass act as anchor points where ice crystals begin to form, shaping the early pattern that spreads outward. Each pane becomes unique because indoor conditions constantly change. A shift in humidity, a gust of air, or even a hand passing nearby can alter how frost develops. When examined closely, these patterns reveal the physics of heat transfer, humidity, and air movement in a room. A simple winter window becomes a detailed map of the environment around it. Cold air can create mirages normally seen only in deserts. When air near the ground becomes extremely cold and dense, it bends light in ways that can reshape distant landscapes. Even slight differences in temperature between layers of air can cause light to travel along curved paths instead of straight ones. This bending allows objects that lie below the horizon to appear lifted upward, creating an image known as a looming mirage. Snow-covered landscapes with flat horizons are especially prone to this effect because their smooth surfaces cool the air evenly. Distant trees, buildings, or mountain ridges may appear taller, sharper, or elevated above their real positions. In rare cases, multiple layers of warm and cold air can stack together, creating complex distortions that make objects flicker, stretch, or appear to float. These winter mirages resemble desert mirages in their underlying physics, yet they occur in environments where the air is more stable and the sky clearer. The result is a display where reality becomes subtly rearranged, revealing how sensitive light is to temperature differences. Ice sheets can trap ancient bacteria that wake when warmed. Layers of ice in certain regions accumulate year after year as new snow falls and older snow compresses beneath it. Dust, organic particles, and microorganisms become sealed within these layers, preserved in cold, dark conditions that limit decay. Some bacteria can enter a dormant state in which they survive without food or sunlight for long periods. When scientists drill deep into glaciers or ice sheets, they sometimes find these microorganisms still intact. If the trapped bacteria have not been damaged by freezing, they can revive when exposed to warmer temperatures and moisture in the laboratory. Their survival depends on protective adaptations that shield their genetic material from damage and allow them to remain dormant for extended periods. These findings offer insights into how life endures harsh conditions on Earth, and may suggest how organisms could survive on other cold worlds. Ice does not simply preserve water, it preserves traces of past environments and can store living material that reveals the resilience of life. Winter storms can lift tiny particles into the stratosphere. During intense winter weather, strong updrafts can develop within large storm systems. These currents are powerful enough to carry fine particles of dust, ash, salt, or organic matter far above the usual height of clouds. If the updrafts push these particles high enough, they can cross the boundary into the stratosphere, a region of the atmosphere that is normally difficult to reach. Once there, the particles can remain suspended for long periods because the stratosphere lacks the turbulent mixing found lower down. This distribution of particles influences atmospheric chemistry and can affect how much sunlight the planet absorbs. Scientists track these events to understand how winter storms contribute to long-range transport of materials and to study the impact on climate. Each storm becomes part of a larger cycle that moves matter into regions where it can remain for months or even years. Frozen soil can preserve animal tracks with remarkable detail. When temperatures drop and moisture within the ground freezes, the surface becomes firm enough to record impressions from passing animals with surprising clarity. A track pressed into soft snow or thin ice may melt or deform later, but a track in frozen soil can remain stable for days or weeks. The freezing process locks the shape in place, capturing subtle features such as claw marks, pads, and gait patterns. Researchers and wildlife trackers use these preserved prints to study behavior, population movement, and the presence of species that are rarely seen directly. In some environments, brief thaws can soften the surface just enough to create a perfect impression before the next freeze solidifies it. Each track becomes a moment of motion captured in the ground, revealing details about the size, speed, and direction of the animal. Winter landscapes therefore provide a unique record of wildlife activity that disappears once the soil thaws in spring. Freezing temperatures can cause paints and plastics to behave unpredictably. Materials that function reliably in warm conditions can react in surprising ways when exposed to deep cold. Paints that remain flexible in summer can become rigid enough to crack when the surface beneath them contracts. The pigments and binders within paint may separate slightly in cold weather, altering texture or adhesion. Plastics, which depend on the movement of their molecular chains for flexibility, can lose that movement when temperatures drop. This makes them more likely to snap or deform under pressure. Certain plastics may shrink unevenly, causing joints to loosen or warp. These changes occur because cold reduces molecular motion, altering how materials respond to stress. Designers and engineers must consider these effects when creating objects intended for winter use. The environment forces paints and plastics to reveal their structural limits, reminding us that temperature can turn familiar materials into unpredictable versions of themselves. Snow dunes can form and migrate like small desert dunes. Wind blowing across open snowfields can sculpt the surface into wave-like dunes that resemble those found in sandy deserts. These snow formations develop when loose. Dry crystals are pushed into ridges that grow and move with each gust. Because snow is lighter than sand, even gentle winds can shape it, creating patterns that shift daily. The size of these dunes depends on wind strength, snow type, and terrain. Some remain only a few centimeters tall, while others stretch across large fields. As wind continues to move the snow, the dunes migrate slowly across the landscape, leaving behind trails of altered texture. These shifting shapes provide clues about prevailing wind directions and the stability of the snowpack. Snow dunes demonstrate that frozen water can respond to the same forces that shape deserts, creating landscapes that transform continuously through winter. Winter ocean water can separate into brine channels with complex chemistry. When seawater begins to freeze, the forming ice excludes most of its salt, forcing the salt-rich water into tiny channels within the ice. These brine-filled pockets create a network of narrow pathways that weave through the frozen surface. The liquid inside remains unfrozen because the high salt content lowers its freezing point. As temperatures fluctuate, the channels expand or contract, altering how water and salt move through the ice. Microorganisms thrive in these narrow spaces, forming small ecosystems adapted to extreme cold and unusual chemical conditions. These brine channels also influence how sea ice grows and melts. The brine can drain downward into the ocean, changing the density of the water below and affecting local circulation. Winter sea ice is therefore not a simple solid sheet. It is a complex structure with hidden liquid pathways and active biological activity that plays a significant role in polar marine environments. Ice can fracture with the energy of small seismic events. During extreme cold, large sheets of ice on lakes, rivers, and coastal regions expand and contract as temperatures rise and fall. When the stress within these sheets becomes too great, the surface can crack with remarkable force. The sudden release of tension sends vibrations racing through the ice and into the water and ground beneath it. Sensitive instruments positioned near frozen bodies of water often register these events as tiny quakes, because the energy travels in a similar manner to seismic waves. People standing on or near the ice may hear booming, rumbling, or whipping sounds that echo across the surface. In wide expanses, the fractures can propagate for long distances, creating visible lines that stretch from one shore to another. These events are shaped by the thickness of the ice, the rate of temperature change, and the movement of water below. Each fracture is a reminder that frozen landscapes are in constant motion, storing and releasing energy in ways that resemble much larger geological processes. Winter storms can create rare spherical ice pellets. When strong cold season storms pull moist air into freezing layers of the atmosphere, unusual forms of precipitation can develop. Among these are small round pellets made of tightly packed ice that form when supercooled droplets collide and freeze around a central particle. As the pellets tumble through turbulent air, more droplets adhere and solidify, building smooth spheres instead of jagged crystals. These pellets differ from hail because they form at lower altitudes and do not require the powerful updrafts found in warm season storms. They also differ from sleet because their internal structure is layered and dense rather than solid through and through. When they reach the ground, the pellets bounce rather than shatter, creating a distinctive sound as they strike hard surfaces. These events happen only under a narrow combination of temperature, humidity, and atmospheric motion, which makes them an uncommon feature of winter weather. Their formation reveals the complexity hidden inside storm clouds, where water and ice interact in constantly shifting conditions. Snowpack can hide vast amounts of water that release suddenly in spring. As snow accumulates through winter, it holds enormous quantities of frozen moisture within its layers. The density of snow changes over time as grains fuse and settle, hiding significant water content beneath what may appear to be a soft, lightweight surface. In regions with deep winter snowfall, this stored moisture becomes a major contributor to rivers, lakes, and groundwater once spring arrives. When temperatures climb quickly, meltwater can flow faster than the soil can absorb it, causing rapid rises in streams and sudden flooding. Mountain regions are particularly sensitive to this process because elevation changes influence how fast different slopes warm. Snowpack also shifts its internal pathways as it melts. Channels develop that guide water downhill in concentrated flows. Scientists monitor snow depth, density, and temperature to predict how much meltwater will enter watersheds. These predictions are essential for managing reservoirs, flood risks, and agricultural planning. Snowpack is therefore not simply seasonal decoration, it is a massive temporary reservoir that plays a central role in the yearly water cycle. Frozen lakes can trap methane in clear domes. When organic matter at the bottom of a lake decomposes, it releases methane that rises toward the surface. In warm months, the gas escapes freely into the atmosphere. During winter, however, a thick layer of ice blocks the release. Gas bubbles collect beneath the frozen surface, pushing upward and stretching the ice into curved, transparent domes. These domes vary in size depending on the amount of trapped gas and the strength of the ice. In some regions, dozens or even hundreds of these structures appear across a single lake, forming a landscape filled with glass-like bubbles suspended in frozen sheets. The trapped methane creates patterns of stacked circles within the ice, each representing a separate pulse of gas. When spring arrives, the ice breaks apart and the gas finally escapes. Researchers study these formations to understand methane emissions and to monitor how lake ecosystems change during winter. The frozen domes act as natural archives of biological activity that continues quietly beneath the ice. Birds adjust their flight patterns based on winter air density. Cold air becomes denser as temperatures drop, increasing lift on bird wings and changing how air flows around their bodies. Many species alter their wing beats, gliding intervals, and flight paths to take advantage of these seasonal differences. Some birds can glide longer distances in winter without expending as much energy because the denser air provides stronger support. Others adjust their altitude to remain within layers where flight efficiency is highest. Even slight shifts in density can influence how flocks coordinate their movements, affecting spacing and formation stability. Birds that migrate through cold regions must account for these changes as they navigate long routes. The mechanics of flight become subtly different from those in warmer seasons. Observations reveal that birds use winter air as a tool, modifying their behavior to maintain speed, conserve energy, and avoid turbulence. Each movement reflects a deep familiarity with the invisible physical environment that surrounds them. Winter can change how radio waves travel. Cold season atmospheric layers often become stratified with sharp differences in temperature between the ground and higher altitudes. These layers can guide radio waves along curved paths that allow them to travel farther than usual. Inversions, where cold air lies beneath warmer air, create a reflective boundary that helps radio signals bounce horizontally instead of escaping upward into space. This effect can strengthen communication signals across large distances during winter nights. At the same time, reduced humidity and clearer air can allow certain frequencies to propagate with less interference. These conditions lead to unexpected reception of distant broadcasts, sometimes hundreds of miles from their origin. Engineers and researchers study these seasonal changes to improve communication systems and to understand how atmospheric structure affects signal pathways. Winter, with its unique temperature gradients, becomes a natural laboratory that reveals how electromagnetic waves interact with the environment. Snow can glow under ultraviolet light. The surface of fresh snow contains countless ice grains that scatter light in all directions. Under ultraviolet radiation, some of these grains reflect and refract wavelengths that create a faint glow visible under the right conditions. This glow is not visible in normal daylight because brighter visible wavelengths overpower the ultraviolet reflection. In controlled environments or under the clear ultraviolet-rich light of high-altitude winters, the glow becomes more apparent. The brightness depends on the purity of the snow, the shape of the grains, and the quality of the light source. Researchers study this effect to better understand how snow interacts with radiation and how it influences energy balance at Earth's surface. Snow that glows under ultraviolet light serves as an example of the complex ways frozen water can manipulate electromagnetic energy. What appears to be a simple white surface is actually a highly reflective structure capable of scattering a wide range of wavelengths. Ice crystals inside clouds can float for long periods without falling. Under specific conditions, small crystals form in cloud layers where temperature, humidity, and air motion remain remarkably stable. These crystals are incredibly light and often shaped in ways that increase drag, slowing their descent. Gentle upward currents within the cloud can counteract the pull of gravity, keeping the crystals suspended for long periods. While suspended, they continue to grow by collecting water vapor from the surrounding air. Some remain aloft until they merge with other crystals or encounter a region where air motion changes. Their long residence time affects cloud brightness, precipitation development, and the way sunlight interacts with the atmosphere. Scientists analyze these suspended crystals to better understand cloud dynamics and weather prediction. The crystals act as tiny tracers that reveal how air moves inside storm systems and high-altitude cloud decks. Winter temperature swings can carve grooves into stone. Rock surfaces expand slightly when warmed by sunlight and contract when exposed to freezing night temperatures. Over repeated cycles, the outermost layers of the rock weaken as microscopic cracks open and close. When water enters these cracks and freezes, it expands, widening the gaps and lifting small flakes from the surface. Over time, this process can produce grooves, pits, or channels that mark the stone with patterns shaped entirely by temperature. These features develop faster in regions where winter brings rapid shifts between warm afternoons and freezing nights. Different types of rock respond uniquely depending on mineral composition and existing structural weaknesses. The changes happen slowly but persistently, revealing the power of winter to reshape solid material through repeated thermal stress. The resulting patterns serve as historical records of the environmental conditions that sculpted them. Snow cover can shift Earth's reflectivity dramatically. Large areas covered with bright, fresh snow reflect a significant portion of incoming sunlight back into space. This increased reflectivity cools the surface and influences the temperature of the air above it. When snow persists across wide regions, it becomes a major factor in the global energy balance, affecting how much solar energy the planet absorbs. Even small changes in snow extent can alter regional climates by modifying the amount of heat transferred between land and atmosphere. Scientists monitor snow cover closely because it interacts with cloud formation, storm tracks, and long-term climate trends. Snow acts as both a shield that deflects sunlight and a regulator that controls surface heating. Its presence or absence can determine whether cold conditions intensify or weaken. Winter landscapes, therefore, hold a powerful role in shaping temperature patterns across much larger scales than the areas they physically cover. Ice can develop layers that store decades of atmospheric chemistry. When snow settles on the surface year after year and slowly compresses into ice, each seasonal layer traps tiny samples of the atmosphere from the moment it formed. These layers hold traces of gases, dust, pollen, volcanic particles, and even microscopic organisms that drifted through the air at the time. As more layers form above, the deeper ice becomes a chronological archive preserved under cold, stable conditions. Scientists drill long cylinders called ice cores to study the chemical signatures locked inside. Each layer can reveal details about past temperatures, atmospheric composition, and environmental events such as forest fires or distant eruptions. Some cores extend back through centuries, allowing researchers to reconstruct long-term climate patterns. The chemical makeup of each layer provides clues about ocean circulation, solar activity, and shifts in vegetation. Ice therefore functions as both a physical material and a record keeper. It captures information that no instrument could have measured in real time and preserves it for generations, offering a detailed window into the history of Earth's atmosphere. Winter air can alter the taste of food. Cold, dry air changes how aromas travel from food to the nose, which affects flavor perception. Aromas rely on volatile compounds that evaporate easily in warm conditions. When the air becomes cold and still, fewer of these compounds rise from the food, leading to a weaker scent. Because a significant portion of what we call taste comes from smell, the reduction in aroma makes certain foods seem less intense. At the same time, cold air can heighten sensitivity to particular flavors, because the mouth and nasal passages remain cool, reducing interference from humidity. This shift is noticeable outdoors during winter activities, or in homes with significant drafts. Foods that normally feel rich may seem muted, while sharper or saltier items may stand out more. The surrounding environment plays a major role. A warm drink tastes stronger when held in cold air, because steam carries aroma directly upward, but a cool dish may seem bland because the scent stays close to the surface. Winter therefore influences flavor by changing the physics of odor molecules and the way the senses interact with the environment. Frost can grow outward from warm objects. When a warm object sits in very cold air, moisture from the surrounding environment can condense on its surface and freeze in place. As heat slowly leaves the object, the frozen layer thickens. Meanwhile, new moisture from the air lands on the thinning warm boundary around the object and freezes just beyond the previous layer. This process continues until delicate icy fingers extend outward, sometimes forming long, feathery structures that reach into the air. The shape of these structures depends on airflow and temperature gradients. If air moves consistently in one direction, frost grows like a miniature forest, leaning toward the flow. If the air is still, the pattern becomes more symmetrical. Frost often forms on pipes, wires, and vents, because they release enough warmth to draw moisture toward them while still remaining cold enough for freezing. These growth patterns highlight the complex balance between heat loss, humidity, and surface temperature. They are visible reminders that frost is an active process shaped by the movement of energy rather than a simple static coating. Winter water can freeze into column structures that look man-made. Under specific conditions, water freezes in vertical columns instead of forming a uniform sheet. This happens when cold penetrates the ground quickly from above, while the soil beneath still contains liquid water. As the surface freezes, ice crystals grow downward, drawing water upward through narrow pathways. The upward flow continues until the crystals lengthen into parallel columns that sometimes stand several centimeters tall. These structures are known for their striking appearance, resembling tiny pillars or raised platforms. They can lift stones, soil, and plant material as they rise, creating uneven terrain that crunches underfoot. The growth of these columns depends on soil moisture, temperature, and the rate at which heat escapes from the ground. When the cold persists, the columns become more pronounced. When temperatures fluctuate, they may collapse, leaving scattered fragments on the surface. These formations demonstrate how freezing can reorganize the structure of the ground in surprising ways, shaping the landscape with patterns that look almost engineered. Sea ice can host complex microbial ecosystems. In polar regions, the surface of the ocean freezes into sheets that develop networks of brine-filled channels within them. These narrow pathways contain salty liquid water that remains unfrozen even in extreme cold. Microbes adapted to low light, limited nutrients, and freezing temperatures thrive inside these channels. They form communities that feed on dissolved organic matter and support small organisms that graze on them. As sunlight filters through the ice during late winter and early spring, photosynthetic microbes begin producing energy, which fuels additional growth. These ecosystems contribute to nutrient cycles in polar oceans by releasing compounds into the water below. When the ice melts, the entire community flows into the ocean, creating pulses of biological activity that influence food webs. Despite the harsh environment, these tiny organisms build stable ecosystems inside structures that appear solid and lifeless from above. Their presence reveals that ice is more than frozen water. It is a habitat capable of supporting life with remarkable resilience. Frozen waterfalls can trap the sound of flowing water beneath. When temperatures drop quickly, the outer surface of a waterfall can freeze, while the water inside continues to move. The flowing water creates tunnels, sheets, and hollow chambers within the ice. These pockets trap sound and reshape it as it echoes through frozen layers. The result is a range of tones that differ from the roar of an unfrozen waterfall. Deep resonant hums mix with lighter tapping sounds where thinner ice vibrates. As temperatures shift, new cracks open and old ones close, altering the acoustic character. Listeners standing near these formations can hear water rushing beneath their feet, while the outer surface remains still. The frozen structure becomes a natural instrument with changing acoustics. The phenomenon illustrates how freezing divides moving water from the surrounding environment, while still allowing its energy to resonate invisibly through ice. Snow can convert sunlight into heat through subtle chemical reactions. Snow reflects much of the sunlight that reaches it, but some wavelengths penetrate the upper layers. When light reaches impurities embedded in the snow, such as organic molecules or dust particles, small chemical reactions can occur. These reactions release tiny amounts of heat, warming the surrounding grains. The warming is subtle, but can influence how fast snow reshapes or melts. In regions with high levels of natural or wind-blown organic matter, these reactions may play a noticeable role in the seasonal transition from winter to spring. The interactions between sunlight, snow grains, and chemical impurities create microenvironments within the snowpack that differ from the colder layers around them. Researchers study these effects to understand melt rates, surface chemistry, and the transformation of snow into firmer, granular forms. Snow is therefore not merely passive under sunlight, it actively participates in energy exchange through reactions that help shape its seasonal evolution. Winter storms can shape sand and soil into entirely new formations. Powerful winds during cold months can move dry particles across the ground, carving them into ridges, ripples, and sculpted forms. When temperatures remain below freezing, moisture within the soil acts as a stabilizer, allowing more detailed shapes to form than in warm seasons. Snow mixed with sand can produce layered structures that appear as though they were shaped by hand. Even short bursts of wind can etch patterns across open ground, while longer storms create features that persist through winter. These patterns reveal information about wind direction, strength, and duration. In coastal regions, winter storms can uncover buried layers of sediment by removing loose particles from the surface. In deserts, cold air stabilizes sand grains long enough for them to accumulate into temporary shapes that vanish when warmer weather loosens them again. The landscape becomes a canvas for winter forces, shaped by the combination of frozen ground and persistent wind. Cold air can reveal heat signatures invisible at other times of year. When temperatures fall significantly below those of objects on the ground, even subtle sources of warmth stand out. Buildings, vehicles, trees, and even buried pipes release heat into the surrounding cold air. These temperature differences create visible patterns when viewed with thermal imaging, highlighting details that remain hidden during warm seasons. Wildlife paths become easier to detect because animals leave warm traces in the snow or air. Human activity also becomes more identifiable as footprints, exhaust, and body heat create distinct thermal signatures. Researchers use these winter conditions to map heat loss in structures, study animal movement, and observe how heat flows through soil and vegetation. The cold environment amplifies thermal contrasts, turning the landscape into a detailed map of energy transfer. Winter therefore provides a unique perspective on the movement of heat through natural and human-made environments. Ice can split rock through repeated freezing cycles. When water seeps into small cracks in stone and freezes overnight, it expands with enough force to widen the opening. If this happens repeatedly throughout winter, the cumulative effect can pry apart layers of rock and eventually break pieces free. This process works slowly but consistently, reshaping cliffs, boulders, and exposed rock faces. The expansion of freezing water creates wedges that push outward with surprising strength. Over time, rocks fracture along natural weaknesses, creating debris that collects at the base of slopes. In regions with frequent freeze and thaw cycles, this process becomes a major factor in the formation of loose stones and soil. It also contributes to the long-term shaping of mountains and valleys. Each cycle adds a tiny change that builds over many seasons, demonstrating the power of winter to transform even the hardest materials. Winter landscapes can develop natural acoustic amplifiers. When snow, ice, and cold air combine in the right proportions, entire landscapes begin acting like giant sound-shaping structures. Fresh, dry snow absorbs high-pitched noises, while reflecting lower frequencies, creating pockets where certain sounds become clearer. Smooth ice on lakes reflects sound efficiently, allowing vibrations to travel across the surface for long distances. Valleys filled with cold, dense air can trap sound between their walls, guiding it along narrow channels. Even frozen forests contribute, because stiff branches transmit vibrations differently than their flexible summer forms. In extremely calm conditions, temperature inversions can form ceilings of warm air above cold surfaces. Sound that would normally disperse upward instead bends back downward, amplifying distant noises. A crack in the ice, a far-off animal call, or a single footstep can seem unnaturally loud. These environments become temporary acoustic chambers shaped entirely by temperature, density, and surface texture. Winter transforms open spaces into resonant stages where sound behaves in surprising ways, revealing the hidden geometry of the landscape. Frozen tundra can preserve ancient forests below the surface. In cold northern regions, the ground can remain frozen for thousands of years, locking entire ecosystems inside it. Long ago, forests of spruce, birch, and other species grew in areas that are now treeless expanses of tundra. When climates shifted and temperatures dropped, these forests died back and became buried under layers of sediment, peat, and ice. The frozen ground protected the remains from decay by halting microbial activity and sealing out oxygen. Tree trunks, roots, leaves, and even seeds can remain intact beneath the surface, preserved in remarkable detail. Researchers who study these buried forests examine the shape of roots, the composition of wood, and the surrounding soil to reconstruct ancient landscapes. Some sites reveal clear evidence of past fires or insect activity that occurred before the freeze. These frozen remains serve as records of climate change that unfolded over long spans of time. They demonstrate how quickly ecosystems can shift and how effectively cold environments can preserve the past. The tundra acts as a vault that stores evidence of forests that once thrived where none stand today. Lakes can freeze so transparently that the bottom becomes visible. In certain regions, cold, dry air pulls heat rapidly from lake surfaces, allowing ice to form with very few trapped bubbles or impurities. When the water beneath is calm and clear, the ice solidifies into a sheet that looks like glass. People standing on such a lake may feel as if they are walking on air, able to see rocks, plants, and fish far below. The transparency depends on cooling rates, clarity of the water, and the absence of wind that would otherwise disturb the surface. As the ice thickens, internal stresses create long fractures that appear as dark lines winding across the frozen surface. These cracks do not break the ice completely, but serve as pathways for stress to release. Some light passing through the ice refracts in unique patterns, creating shifting bands of brightness on the lakebed. In some places, trapped methane bubbles freeze into layers, creating white circular patterns beneath the surface that contrast with the clear ice. These transparent lakes offer rare views into aquatic ecosystems during winter, turning the frozen surface into a window rather than a barrier. Snow lines across mountains can map wind currents with precision. When wind sweeps across rugged terrain, it redistributes snow in patterns that reflect its strength, direction, and persistence. Ridges that face into the wind often remain bare, while sheltered slopes accumulate deep drifts. Thin streaks of snow can form along contour lines, where the wind loses just enough speed for crystals to settle. These lines reveal the structure of airflow sliding across the mountain surface. In exposed passes, snow may gather only in narrow bands that align with channels of reduced turbulence. Researchers and mountaineers read these snow lines to understand how winter winds interact with the landscape. They provide clues about avalanche risk because areas with uneven loading are more prone to sudden shifts. Over time, the pattern of snow accumulation builds a detailed map of winter airflow that changes with each storm. These natural markers demonstrate how mountains divide, guide, and reshape the wind, turning invisible currents into visible tracks etched in white across the slopes. Winter storms can rearrange ocean layers temporarily. Powerful cold season storms generate strong winds and pressure changes that churn the upper layers of the ocean. This turbulence mixes warm surface water with cooler, deeper water, disrupting the usual layering that forms through summer heating. Storm-driven waves and currents push water sideways and downward, forming temporary pathways that transport heat, salt, and nutrients. In regions influenced by ocean currents, winter storms can redirect surface flow, altering the position and strength of these currents for days or weeks. When the storm passes, the ocean does not immediately return to its previous state. Instead, it rebuilds its layered structure over time as temperature and salinity differences re-establish themselves. Marine organisms respond to these changes. Nutrients lifted from deeper layers can trigger short bursts of productivity, while sudden cooling or mixing can shift the behavior of fish and plankton. Winter storms, therefore, play a major role in shaping the ocean's internal structure, influencing conditions that persist long after the surface has calmed. Ice can grow in feathers and fans instead of sheets. Under certain temperature and humidity conditions, water vapor does not form a uniform layer of frost. Instead, it assembles into branching structures with delicate feather-like patterns. These shapes appear when the vapor attaches to surfaces at angles that encourage growth in one direction more than another. As the crystal grows, each branch extends outward and divides into smaller segments, creating a fan of tiny blades. These formations often appear on windows, metal surfaces, and even smooth stones. Slight differences in temperature across the surface guide the direction of growth, while airflow shapes the length and thickness of each branch. The resulting patterns resemble organic forms, even though they arise from physical processes controlled by molecular arrangement. People who observe these ice feathers often notice that no two are alike. Each one records a unique combination of temperature, humidity, and surface conditions. Winter reveals the capacity of water vapor to create intricate crystallized art that changes from hour to hour. Winter conditions can dramatically change how animals communicate. Cold air travels differently across landscapes than warm air, altering how sound moves and how far it carries. Many animals adjust their calls, chirps, or howls to suit winter conditions. Some species produce deeper or slower sounds because these frequencies travel farther in dense cold air. Others shift their activity to times when wind is minimal, so their signals reach intended recipients more clearly. Snow cover also plays a role. It absorbs high-pitched noises while reflecting lower ones, changing the acoustic environment that animals rely on. In forests, rigid frozen branches transmit vibrations differently than flexible summer foliage, influencing how animals gauge distance or respond to threats. Even scent-based communication changes, because cold air preserves certain chemical signals that would dissipate quickly in warm weather. Winter becomes a season where communication strategies adapt to the physical properties of the environment. Each species responds differently, revealing a wide range of behavioral flexibility shaped by cold temperatures. Snow cover can shift temperatures in nearby cities. A thick layer of snow reflects sunlight that would normally warm the ground, causing surface temperatures to remain lower for longer periods. When this reflective surface surrounds urban areas, it influences how heat flows in and out of cities. Cold air from snow-covered regions can drift into populated areas, lowering temperatures and altering wind patterns. Snow also reduces the amount of heat that buildings and roads absorb during the day, which means cities release less warmth at night. This changes the intensity of the urban heat island effect, sometimes flattening the usual temperature difference between cities and rural surroundings. Snow-filled parks, fields, and riverbanks become cool zones that influence air circulation on a neighborhood scale. As the snow melts, the release of moisture further modifies local conditions. Urban planners and meteorologists monitor these interactions to understand how winter landscapes reshape city climates. Snow does not stay at the edges of cities. It becomes part of the temperature system that influences everything from energy use to daily weather. Frozen air can create visible shock waves around moving objects. When temperatures drop far below freezing, the air becomes dense enough that sudden movement can compress it into visible patterns. Fast-moving objects such as birds, vehicles, or thrown snowballs can generate faint lines or puffs of condensed moisture where the air pressure changes abruptly. These shock patterns appear because cold air holds very little water vapor, so even slight changes in temperature or pressure can force the moisture to condense briefly. The result is a faint white outline that trails or surrounds the moving object for a moment before fading. In extremely cold regions, people may see the effect when exhaling forcefully, throwing boiling water into the air, or swinging an object rapidly. Each event demonstrates how cold air responds sharply to movement, creating visible traces of pressure that would be invisible in warmer conditions. Winter reveals physical behaviors of the atmosphere that remain hidden during other seasons. Winter fog can become so cold that it forms crystals mid-air. In certain conditions, tiny droplets within fog remain supercooled, meaning they stay liquid even though temperatures are well below freezing. When these droplets encounter dust particles, snowflakes, or even gentle disturbances, they can freeze instantly. The freezing process transforms the fog into a floating field of ice crystals that sparkle as they drift through the air. Unlike snowflakes formed high in the atmosphere, these crystals originate close to the ground and fall slowly, creating a shimmering curtain that moves with the breeze. This transformation can happen suddenly, turning ordinary fog into an icy display that looks otherworldly. The crystals often collect on exposed surfaces, forming delicate frost that grows in the direction of the wind. The event demonstrates how sensitive supercooled droplets are to subtle changes in their environment. Winter fog becomes a stage for rapid freezing processes that reveal the fine boundary between liquid and solid in the natural world. Frozen ocean waves can store energy that releases when thawed. In polar regions, waves continue to move beneath the surface, even as the upper layer freezes. When temperatures drop fast enough, the tops of these moving waves solidify into curved ridges that hold the shape of the motion below. These frozen waves preserve patterns of force that were present at the moment they formed. The ice flexes slightly with continued movement of the water underneath, storing mechanical stress just as a bent branch stores tension. As sunlight returns and the ice begins to soften, these stresses release in small bursts that cause cracks, pops, and shifts along the frozen surface. In some cases, the thaw can reveal hidden ridges that collapse suddenly, creating short-lived jolts that ripple across the weakening ice sheet. Researchers study these stored energy patterns to understand how sea ice responds to winter storms and ocean circulation. Frozen waves become records of past motion and future instability, showing how closely connected ice is to the water that shaped it. Winter skies can generate extremely rare atmospheric arcs. On the coldest days, tiny ice crystals suspended in the air can interact with sunlight in ways that create arcs far more complex than ordinary halos. These crystals often take the form of flat plates or narrow columns that drift in gentle alignment, allowing light to bend through them in predictable arcs. When conditions are perfect, multiple arcs can appear at once, forming loops, curves, or split bands at unexpected angles across the sky. These displays depend on the orientation of the crystals and the altitude of the sun. Some arcs form only when the sun is low, while others appear briefly as the angle changes. The colors can range from faint white to strong hues that resemble thin ribbons of light. Scientists classify these arcs by analyzing the geometry of the crystal shapes that create them. Most people never see these patterns because they require air that is extremely cold, clear, and filled with just the right type of crystals. Winter occasionally turns the sky into a complex optical instrument, projecting patterns created by the frozen air itself. Snow depth can determine where entire species migrate. Animals that travel long distances each year rely on environmental cues to choose safe and productive routes. One of the most important of these cues is the thickness of snow on the ground. Deep snow slows movement, hides vegetation, and increases energy expenditure for herbivores and carnivores alike. As a result, some species shift their migration paths based on where snow accumulates. Caribou, for example, avoid areas with deep powder because it restricts access to the lichen they feed on. Predators follow these changes, adjusting their hunting routes to match the movement of their prey. Birds that rely on ground feeding avoid regions where snow is too thick to uncover food. Even small mammals alter their paths, seeking routes where snow is shallow enough to travel through or deep enough to burrow under for shelter. Long-term climate shifts influence snow depth across continents, which in turn reshapes migration corridors. Snow therefore acts as a map that guides animals towards survival. Frozen ground can shape rivers long before spring thaw. When temperatures fall, moisture within the soil freezes and expands, altering the structure of the ground. This expansion can raise sections of soil, redirect surface water, and change the path that meltwater will eventually take. During winter, small streams may shift sideways as frozen soil blocks their usual channels. Ice can anchor fallen branches or debris that accumulate into natural dams. These blockages shape the distribution of water beneath snow layers, guiding it into new routes. By the time spring arrives, the snowmelt follows pathways that winter has already prepared. Frozen soil also affects erosion. Hard ground resists the flow of water early in the season, causing streams to cut deeper into thawed sections instead. Over many years, these repeated winter effects can permanently shift a riverbed. The landscape changes even during months when everything appears frozen solid. The ground is constantly preparing the shape of future waterways long before the ice melts. Winter storms can leave behind patterns that map their path. After a major storm, the distribution of snow across a landscape often carries a clear imprint of how the system moved. Bands of heavy snow mark regions where strong upward motion occurred, while lighter zones trace areas with weaker lifting. As winds wrapped around the storm, they sculpted drifts that align with the flow of air near the surface. These drifts reveal details about wind speed, direction, and turbulence at specific moments during the storm. Icy ridges and compacted layers show where the storm paused or shifted. Melt patterns that appear shortly after the storm can indicate which areas received bursts of warmer air or sunlight through breaks in the cloud cover. Meteorologists use these signatures to reconstruct the movement of storms in regions without direct observations. Nature records the path of each winter system in the shapes, layers, and contours left behind on the ground. The storm may pass quickly, but its imprint remains visible to anyone who knows how to read the clues. Ice can form double layers with different properties. When water freezes in stages, it can create distinct layers of ice that differ in clarity, strength, and texture. The first layer forms under calm conditions and tends to be clear because impurities have time to settle. Later, as temperatures fluctuate, a second layer may form on top with trapped bubbles or uneven crystal growth. These layers often bond together, yet retain their unique qualities. The lower layer may be strong enough to support weight, while the upper layer remains fragile. In lakes, these differences affect how cracks spread and how sound travels across the surface. Sunlight penetrates each layer differently, creating variations in brightness and color. Temperature shifts can cause the layers to expand or contract at different rates, producing faint popping sounds or small shifts along the boundary between them. Double-layered ice provides clues about the weather history of a location, recording calm nights, windy days, and freezing events in separate strata. Snow blankets can hide volcanic gases until they melt. Active volcanic regions often release gases through small vents, cracks, and porous ground. During winter, deep snow covers these openings and traps the gases beneath a thick insulating layer. The snow prevents the gases from dispersing into the air, allowing them to accumulate in pockets with unique chemical compositions. When warmer weather arrives or sunlight softens the snow, these gases are released in short pulses. Researchers use these emissions to study volcanic activity because they contain information about chemical processes occurring deep below the surface. Snow can also filter particles from the gases, leaving behind mineral deposits that appear when the snow melts. In some places, the heat from rising gases melts small tunnels upward through the snowpack, forming vents that resemble tiny chimneys. These features reveal where the ground beneath remains active even during the coldest months. Snow does not silence volcanic activity, it simply hides it until conditions allow the gases to emerge again. Frozen lakes can amplify vibrations miles away. A wide expanse of ice covering a lake behaves like a resonant surface, capable of transmitting sound across long distances. When a force strikes the ice, the resulting vibrations travel outward in waves that maintain their energy efficiently. People can hear cracks, shifts, or distant footsteps echoing across the surface. Even small events produce surprising reach, because the ice acts as a continuous rigid membrane. The underlying water also contributes. Sound waves that enter the water can reflect back into the ice, reinforcing particular frequencies. Under the right conditions, distant noises that would normally fade become amplified. Researchers use these acoustic properties to study ice thickness, stress distribution, and the movement of water beneath the surface. For anyone standing on a frozen lake, the experience can feel uncanny. The ice becomes a giant instrument that responds to every shift, creating an acoustic environment unlike any other season. Winter pressure changes can alter animal behavior. Atmospheric pressure often fluctuates sharply during winter storms and cold outbreaks. Many animals sense these changes long before humans notice them. Birds may alter their feeding patterns when falling pressure signals an approaching storm. Mammals often seek shelter earlier than usual when rapid pressure drops occur. Fish respond as well, rising or sinking in the water column depending on how pressure affects buoyancy. Insects that remain active in winter adjust their hiding or feeding strategies to avoid exposure during turbulent weather. Even domestic animals display subtle shifts in activity levels when pressure changes dramatically. These responses are adaptive behaviors developed over a long evolutionary history. Pressure variations provide valuable early warnings of changing conditions, especially when severe weather approaches. Winter amplifies these cues because storm systems can be more intense and frequent. Animal behavior becomes a living indicator of atmospheric change. Freezing temperatures can make wood behave like metal. As the water inside wood fibers freezes, the material stiffens significantly. The flexible cell walls lose moisture and become rigid, reducing the ability of the wood to bend. This change gives it a solidity more often associated with metals. A wooden branch that bends easily in summer may snap cleanly in winter when subjected to force. Wooden structures, such as fences or beams, produce sharp sounds when temperature drops quickly, reflecting sudden shifts in internal stress. In extreme cold, impacts on wood can create clear ringing tones instead of dull thuds because of the increased stiffness. Furniture, tools, and structures built from wood must be designed to withstand these seasonal changes. Winter reveals the hidden strength and brittleness that emerge when organic material transitions into a near-metallic state under freezing conditions. Winter cold can lock minerals into place in a way summer never can. When temperatures drop far below freezing, water inside soil and rock pores turns to ice, expanding and forcing mineral grains tightly together. This freezing cements loose particles, stabilizing them in arrangements that would otherwise shift. In fine-grained sediments, the ice binds clay and silt into a rigid structure that resists erosion. In rocky terrain, moisture trapped between mineral grains freezes and forms interlocking bridges that temporarily strengthen the stone. This binding effect can preserve delicate mineral formations or fossil structures that might crumble in warm weather. Researchers studying frozen ground often find minerals frozen in mid-change, held in positions that reveal chemical processes normally hidden in motion. When the thaw comes, the minerals begin to release, and the structure may weaken again. Winter therefore provides a moment of geological suspension, holding minerals in configurations that store clues about the transformation of rocks, soils, and sediments. Cold becomes a natural preservative, capturing the fine details of Earth's interior with precision. Snowfall rates can increase sharply with tiny shifts in temperature. When temperatures hover just below freezing, the atmosphere becomes extremely sensitive to small changes in thermal conditions. A drop of only a degree or two can alter the shape, size, and growth rate of snow crystals. Slight cooling increases the amount of moisture the air can convert into ice, causing snowflakes to grow more quickly as they form. These tiny changes also influence how crystals stick together. In some conditions, they cluster into large flakes that fall faster and accumulate quickly. In other conditions, they form small grains that build up slowly. Storm systems respond sharply to these microscopic differences. Warmer clouds may produce light flurries, while slightly cooler ones generate heavy bursts of snowfall. Meteorologists track these marginal temperatures closely because they can determine whether an area receives a dusting or several centimeters of snow. The sensitivity of snowfall to small thermal shifts highlights the complexity of winter weather and the precision needed to understand it. Frozen soil can heat upward through narrow channels. When the upper layer of ground freezes, it does not become a perfect solid barrier. Instead, small cracks and pathways remain where heat from deeper soil continues to escape. These channels guide warmth toward the surface, forming faint thermal lines that can influence the distribution of frost and snow. In agricultural regions, these warm pathways can protect root systems by preventing the soil below from freezing completely. In natural landscapes, they create microhabitats, where insects, microbes, and plant roots remain active even during intense cold. The channels also affect how frost crystals form on the surface, sometimes creating patterns that reflect the invisible flow of heat below. Researchers use thermal imaging to map these pathways, discovering that frozen soil behaves like a network of tiny vents. The process demonstrates that winter does not stop the movement of energy through the ground. Instead, it reshapes it into narrow routes that influence everything above. Ice can preserve footprints for an entire season. When a person or animal steps on thin snow overlying wet ground, the pressure compresses the surface and brings moisture upward. As temperatures fall, this moisture freezes into a firm cast that follows the exact shape of the track. Subsequent snowfalls may cover the footprint, but the frozen imprint beneath remains intact. In regions with consistent cold, these preserved tracks can last for months. They record stride length, foot shape, direction of travel, and even subtle details such as claw marks or the tread of a boot. Wildlife researchers use these long-lasting prints to study movement patterns, territory boundaries, and population behavior. When spring returns and the ice melts, the tracks fade, leaving behind only the briefest trace of their winter life. The ability of ice to preserve impressions provides a natural record of activity that survives long after the moment of passage. Winter storms can collect atmospheric dust that would otherwise disperse. Strong winds during cold weather can lift fine dust from exposed soil, dried vegetation, and distant landscapes. Instead of falling quickly, these particles can be carried into storm systems, where they mix with ice crystals and snowflakes. As the storm travels, the dust becomes embedded within the precipitation. When the snow finally reaches the ground, it delivers the dust as part of the accumulation. The particles may appear as faint streaks or layers in the snowpack. Researchers analyze these deposits to trace the origins of the dust, which can travel across countries or oceans before settling. Dust captured in snow provides information about soil erosion, volcanic activity, and even pollution far from the snowfall region. Winter storms therefore function as collectors, sweeping up atmospheric material that would normally disperse invisibly. The dust becomes part of the winter landscape, stored within the snow until it melts. Frozen vegetation can act as natural fiber optics for sunlight. When plants freeze, the water inside their cells forms ice that becomes surprisingly transparent. Sunlight entering frozen stems or leaves can travel through the ice-filled structures, bending along their internal pathways. The effect resembles fiber optics, where light moves through narrow channels with little loss. Frozen grasses and twigs can glow as sunlight passes through them, creating bright or shimmering edges during sunrise or sunset. The visual effect depends on the clarity of the ice, the angle of the sun, and the internal structure of the plant. In some cases, the light refracts outward, producing halo-like glints that appear at specific angles. The phenomenon reveals how freezing alters the optical properties of organic material. In warm seasons, light scatters through water-filled and pigmented tissues. In winter, ice transforms vegetation into a temporary network of light-guiding structures. Snow cover can alter the path of groundwater. A thick blanket of snow insulates the ground and changes the timing and location of water entering the soil. When spring arrives, snow melts unevenly depending on slope, sunlight exposure, and vegetation. The resulting meltwater may flow along the surface briefly before seeping into the ground at specific entry points. In regions with frozen subsoil, the water cannot penetrate deeply and instead spreads sideways, forming new channels. These changes influence how groundwater replenishes aquifers and how streams respond to seasonal flow. Over many years, repeated patterns of snowmelt can carve long-term pathways that guide water to certain areas while leaving others dry. Hydrologists track these seasonal shifts to understand how winter affects water availability. Snow becomes a major factor in shaping underground water systems, guiding the movement of water long after the season has passed. Winter can cause metals to contract enough to change mechanical systems. As temperatures fall, the atoms in metal slow their movement and draw closer together, causing the material to shrink. The amount of contraction varies by metal type, but can be significant enough to alter how mechanical parts fit together. Bolts may loosen, gears may shift out of alignment, and joints may tighten unexpectedly. In large structures, contraction can produce audible creaks as metal beams adjust to the cold. Machines designed for year-round use often require special materials or tolerances to ensure they function reliably in winter. The contraction effects also influence bridges, railways, and pipelines, which must endure repeated cycles of shrinking and expanding. Engineers account for these seasonal changes when designing equipment and infrastructure. Winter demonstrates that even seemingly rigid metals respond to temperature with subtle but important movement. Ice sheets can generate vibrations that resemble deep ocean sounds. When large ice fields expand or contract, they produce low-frequency vibrations that travel for long distances through both ice and water. These vibrations occur when the ice cracks, shifts, or grinds against itself. Instruments placed near polar regions often detect these sounds as long droning tones or rhythmic pulses. Although the vibrations originate in ice, they resemble sounds produced by ocean currents or underwater geological activity. Scientists study these signals to understand how ice sheets behave under stress and how they respond to temperature changes. The vibrations provide clues about the formation of cracks, the movement of ice shelves, and the stability of frozen landscapes. Winter turns ice into an acoustic landscape that reveals its hidden motion through deep, resonant tones. Snow can sublimate directly into the air without melting. When temperatures remain below freezing but the air is dry, snow can transition straight from a solid to a gas. This process occurs when sunlight or wind provides enough energy for ice molecules to escape into the atmosphere without forming liquid water. Sublimation can thin snow layers gradually, leaving behind sharp edges or unusual surface textures. In mountain regions, it can reduce snowpack significantly even during cold spells. The process also influences humidity, as the vapor contributes to the moisture content of the air. Scientists study sublimation to understand how snowfields shrink, how much water enters the atmosphere, and how energy moves through winter landscapes. It is a reminder that snow does not require warmth to disappear. Cold, dry conditions can remove it just as effectively through a completely different physical pathway. Frozen landscapes can create sudden cold air sinks that move downhill. When winter nights become especially clear and still, the ground loses heat rapidly to the atmosphere. As the surface cools, the air immediately above it grows denser and heavier. This dense cold air begins to slide downhill under the influence of gravity, flowing through valleys and ravines like an invisible river. These cold air sinks can form quickly, often within minutes, and they can push temperatures in low-lying areas far below those found on surrounding slopes. Farmers and ecologists monitor these flows because they can damage sensitive vegetation or create microclimates that influence where certain species grow. In mountainous terrain, cold air pools can persist for hours, forming pockets of extreme cold even after sunrise. The movement of these air masses demonstrates how winter transforms the atmosphere into a dynamic fluid that responds directly to subtle temperature shifts. The landscape becomes a channel for cold, guiding it through contours and depressions with surprising speed. Snowpack chemistry can change based on tiny differences in sunlight. Snow appears uniform from a distance, yet its chemical makeup evolves constantly as it absorbs varying amounts of sunlight. Even slight changes in angle, cloud cover or shading can alter how quickly snow grains warm. As grains warm, thin films of liquid water form on their surfaces, allowing gases and dissolved substances to move between layers. Sunlight can also trigger chemical reactions within impurities such as organic molecules, trace minerals, or atmospheric pollutants. These reactions release or transform compounds that migrate through the snowpack, creating chemical gradients shaped entirely by light exposure. In forests, the canopy breaks sunlight into patchy patterns, causing neighbouring snow patches to develop very different chemical profiles. In open areas, the angle of the sun across the day creates waves of chemical change from morning to afternoon. By spring, the snowpack becomes a mosaic of zones with distinct chemical histories. Researchers examine these patterns to understand nutrient cycles, atmospheric deposition, and the processes that influence spring meltwater quality. Winter storms can push snow high into mountain passes without wind. Some storms generate strong vertical motion that lifts snow upward rather than sideways. In these events, moist air rises rapidly over mountainous terrain, cooling and condensing into dense snow formations. Instead of being blown by strong winds, the snow is carried upward by the rising air itself. This process can deposit large amounts of snow in elevated passes and saddles, even when surface winds remain calm. The effect becomes most pronounced when warm moist air meets cold mountain air, creating buoyant upward motion that lifts snow into paths that defy normal expectations. Mountaineers sometimes find deep drifts in sheltered high areas that experience no wind during the storm. These drifts reveal the power of vertical atmospheric movement in winter conditions. The snow distribution becomes a map of where air currents rose, stalled, or cooled, showing how storm structure influences the landscape in ways that surface observations cannot predict. Frozen lakes can crack along perfect geometric lines. When ice forms evenly across the surface of a lake, it contracts as temperatures fall. This contraction creates stress that must release through fractures. Instead of breaking randomly, the ice often cracks along geometric patterns, such as long straight lines intersecting fans or triangular grids. These shapes arise because the ice sheet behaves like a rigid plate with uniform thickness. Stress concentrates at symmetrical points, causing fractures to propagate in predictable directions. The resulting patterns can span large portions of the lake, creating networks that look intentional. When sunlight hits these cracks, reflections reveal sharp edges that contrast with the smooth ice. The sounds produced during cracking can echo across the lake as deep booms and sharp snaps. Each pattern represents a moment when the ice released tension stored over hours or days. Scientists study these shapes to understand mechanical stress in frozen materials and to assess ice thickness. The winter lake becomes a canvas of geometric tension. Winter conditions can change how seeds survive underground. Beneath snow and frozen soil, seeds wait in a state of deep dormancy. Winter conditions determine which seeds survive until spring. Some species require prolonged cold exposure to trigger the biochemical changes that allow them to germinate later. Others benefit from snow insulation, which shields them from extreme temperature swings that would otherwise damage their tissues. Moisture locked in frozen soil can preserve seed coats, preventing rot during long dormant months. In regions with alternating freeze and thaw cycles, the expanding and contracting soil can bury seeds more deeply or bring them closer to the surface, influencing where they eventually sprout. Even subtle differences in soil temperature across a landscape create microclimates where certain seeds survive better than others. Winter therefore shapes plant communities long before growth begins. The cold acts as both a filter and a catalyst, determining which species emerge when warmth returns. Ice can form lenses that start small fires when sunlight returns. Under the right conditions, clear ice can act as a natural magnifying lens. When water freezes without air bubbles or impurities, it creates a smooth curved surface capable of focusing sunlight into a concentrated point. During late winter or early spring, when the sun climbs higher in the sky, these ice lenses can direct intense beams of light onto dry vegetation. The focused heat can raise temperatures enough to ignite small fires, especially in regions where sunlight remains strong, but fuels are dry from winter chill. This phenomenon is uncommon, but documented in areas with highly transparent ice formations. The effect demonstrates how freezing can create unexpected interactions between light and the environment. Ice becomes both a cold surface and a powerful optical device once the sun reaches the correct angle. Winter air can reveal hidden heat leaks in buildings and terrain. Cold air creates sharp temperature differences between warm structures and the surrounding environment. When viewed with thermal imaging, these differences become visible as bright patches where heat escapes from buildings. Poor insulation, gaps around windows, and structural weaknesses reveal themselves clearly. The same principle applies to natural terrain. Warm groundwater springs, decomposing vegetation, and burrowing animals create warm spots that stand out against the frozen landscape. Surveyors, architects, and researchers take advantage of winter conditions to pinpoint inefficiencies or hidden processes that remain invisible in warm seasons. The cold simplifies the thermal environment by reducing competing heat sources, making it easier to detect anomalies. Winter air acts as a diagnostic tool, exposing the unseen movement of heat through both human-made and natural structures. Snow can bury scent trails so effectively that predators must adapt. When deep snow falls, it traps and muffles the chemical signals animals leave behind. Scents that linger on the ground during warm seasons become sealed beneath the surface, making it much harder for predators to follow prey. As a result, many predators shift strategies. Some rely more on hearing, listening for movement beneath the snow. Others search for tracks that remain visible on the surface, rather than relying on scent alone. Certain predators wait near known travel corridors where prey must eventually pass, using behavior instead of scent trails to locate food. Prey animals also adapt, taking advantage of the reduced scent transmission to move more freely or choose new routes. Snow transforms the sensory landscape of winter habitats, forcing animals on both sides of the food chain to rethink how they navigate and survive. Winter temperatures can alter water density in ways that protect aquatic life. As water cools, it becomes denser until it reaches a point just above freezing. At this temperature, however, the density begins to decrease again. This unusual property allows cold water to float above slightly warmer water, creating a stable layering effect in lakes and ponds. When ice forms at the surface, it insulates the water below, preventing deeper layers from freezing. This allows fish, amphibians, and countless microorganisms to survive winter in the liquid zone beneath the ice. Even in very shallow bodies of water, this density behavior provides a protective buffer. The layering also slows the movement of water, reducing energy loss and helping maintain pockets of oxygen. Without this unique property, winter would freeze lakes solid, eliminating aquatic life each year. Water becomes a shield that preserves entire ecosystems through the coldest months. Frozen clouds can drift for long periods without producing snow. High in the atmosphere, clouds can contain countless tiny ice crystals, suspended in extremely cold but stable air. These crystals are often too small to fall and remain buoyant because the surrounding air rises just enough to counter gravity. The crystals drift with upper-level winds, sometimes traveling great distances. These ice-filled clouds reflect sunlight strongly, contributing to the brightness of winter skies. They also influence temperature by trapping heat from below. Under the right conditions, they may persist for days without producing precipitation. Their stability depends on humidity, temperature, and the gentle balance of rising and sinking air. Frozen clouds demonstrate that winter precipitation does not form automatically whenever ice is present. The atmosphere must shift in very specific ways before the crystals grow large enough to fall. Until then, they linger silently, shaping winter light and temperature from above. As the last traces of winter settle in your thoughts, the season can fade into something soft and distant. The cold air, the hidden motion beneath ice, the quiet changes inside snow, all of it can slip into the background like a landscape disappearing into twilight. There is nothing left to follow and nothing left to hold, only the gentle stillness that winter carries so easily. If you enjoyed this quiet journey, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. The night feels wide and calm now, and the world has grown simple again. You can let yourself drift at your own pace with no weight and no hurry. Good night.